So let's take a look at much larger systems and how would we solve those systems. So algebraically it can get kind of tedious and bogged down, so to speak. And what we're going to do is simplify this method in a way, or present a method for finding the solution to much larger systems. And I'm going to move up to a system with 3 equations and 3 unknowns. And here, notice I'm going to start introducing, and we'll use it more and more, the variables instead of x, y, z. When we have, 3 or more variables, it gets very difficult to say what the variables will be. So we'll just use subscripts. So the variables here are x of 1, x of 2, and x of 3. And if we need 4 variables, x of 4, and so on. So this system here, what would the solution be? Well, we're going to introduce something known as the augmented matrix for the system. So the matrix is a matrix is an array of numbers. Some of you have dealt with matrices, and we will look at matrices in and of themselves shortly, a little bit more in depth in the properties and the arithmetic involved with those objects. But right now, this is a way of abbreviating the system of linear equations. And see if you see the connection here. What we do is, first of all, make sure our equations are set up so that all the x1 variables are lined up right over each other, then all the x sub 2 variables, then all the x sub 3 variables equals then your constants. So you got to line them up this way in order to create what we call the augmented matrix. So the augmented matrix again abbreviates the system, and all we're doing is we're taking in the first equation the coefficients of the variables in order as we go from left to right. So the coefficient of x sub 1 is 2. Coefficient of x sub 2 is actually negative 3. Notice it's minus 3, which is plus a negative 3. So we do a negative 3 there for the coefficient. Plus 7x sub 3, so 7 is the coefficient there, equals, and then we put the constant term there, 5. So the first 3 are coefficients. The first one corresponds to the coefficient of x sub 1, second one coefficient of x sub 2, third one coefficient of x sub 3, and then the constant term. And then the same thing for the next equation, right? 1x sub 1 plus 4x sub 2 plus a negative 2 times x sub 3 equals 9. 3x sub 1, there's no x sub 2 term there, and so notice the coefficient is 0. I have to put a 0 there. 5x sub 3 equals 0. So this summarizes the system without the variables and the equal sign. And we're going to see this is a very convenient thing to do when we're solving the system, and the algorithms will essentially be working on this augmented matrix as opposed to the system of linear equations. Although, again, whatever we do here, there's a similar activity that we're doing over here, and we'll make that connection. Another thing I just want to introduce when we talk about, in general, systems of linear equations, we often use this notation. So here's a system of m linear equations in n unknowns. We don't know how many equations there are, and we don't know how many unknowns there are. And so what we're going to do is take a look at this. Got somebody at my front door, but hopefully somebody in the house will answer it. The first equation here, all the way down to the m equation. So the mth equation is here, and you can see that the subscript here for the b's, which are the constants, correspond to the equation number. The variables are here, x sub 1, x sub 2, x sub 3, all the way to x sub n. Do you see that? The dot, 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 meaning the pattern continues. And the coefficients, notice A, have a double subscript. So what's that double subscript mean? Well, there's 2 numbers there, 1, 1, 1, 2, and so on. The first number corresponds to the equation number, and then the second number corresponds to the variable it's the coefficient of. So A11 is the coefficient of x sub 1 in the first equation, A12 is the coefficient of x sub 2 in the first equation, A13 is the coefficient of x sub 3 in the first equation, and so on. A21 is the coefficient of x sub 1 in the second equation, A22 coefficient of x sub 2 in the second equation, A23 is coefficient of x sub 3 in the second equation, and so on. Okay, so that's the notation that we use. In general, then the augmented matrix for that corresponding system would look like this. Okay, and we see this pattern, and that's going to be helpful to organize things and to talk about it. So what can we do to solve? Let's go back to this one. How can we solve a system like this? what can we do to solve a system like this? Well, what are the valid things that we can do to solve when we're dealing with equations? I want to think about the substitution and the elimination methods that we looked at in the last video for 2 equations and 2 unknowns. And it turns out that we can simplify the valid operations to a system of linear equations to 3. Number 1, we can take and interchange or swap any 2 equations. We can change the order. Okay, so in other words, this we'll call this top equation here the first equation. This equation is the second equation. This is the third. So I can swap the first and third equation. That doesn't change the solution, the values of the variables that satisfy all 3 equations, right? Because that's what we're looking for when we say the solution. What's the values of x1, x2, and x3 that satisfy or make true all 3 of these equations? So I can swap or interchange. And of course, the corresponding operation for the augmented matrix are what we sometimes call elementary row operations. So in a matrix going across, we call these rows. So this is the first row, corresponds to the first equation, right? Second row and third row. By the way, going down, we call these columns. Okay, so rows are horizontal, going across. I want to make note of that. Columns, vertical, going down. So there's 3 rows and 4 columns in this augmented matrix. Again, the columns correspond to what? The first 3 columns correspond to the coefficients of our variables. The last column corresponds to the constants over here. Each row corresponds to an equation. Okay, so if I interchange 2 equations, that's just interchanging 2 rows. Okay, so that's something we can do. And there's times when we want to do that, and we'll explain in that process a little bit later. We can also multiply both sides of the equation by a non-zero number. And we do that all the time, right? If I'm solving the equation 3x equals 12, 3x equals 12, what do? I divide both sides by 3 or multiply both sides by 1/3, right? And I can do that. That's a valid thing. That doesn't change the solution to the equation. So multiplying, you can also say divide, but we're going to stick with multiply. Multiply both sides of the equation by a non-zero number. Okay, so what's the corresponding row operation? Let's just multiply any row. So you have a row of numbers. If you want to multiply, say I want to multiply both sides of this equation by 2, I would have 6x1 plus 10x3 equals 0. Well, that would just be what? 6, 0, 10, 0. So same thing, multiplying these entries in this row by that constant is the same as multiplying both sides of the equation by a constant. And then adding a multiple of one equation to another, right, as we did in the addition or elimination method, right? So remember, like, maybe looking in here, I might want to say, hey, I can multiply the second equation here by -2, right? -2 times x1, -8x2, positive 16x3, and so on, right? And then I can add equation 1 to this -2 times equation 2. So I can add equation 1 to that. So 2x1 plus a -2x1 would get rid of that x1, right, in the first equation. Of course, what I'm doing is I'm actually changing the first equation. I'm simply adding -2 times the second equation to the first equation. And so what's the corresponding row operation? I can add -2 times the second row to the first row. Okay. Now the textbook has an example if you want to look at on page 7, example 6. I've created one. I'm just going to go through. Don't worry about all the technical details. I just want you to see this. So just sort of sit back and feel this out. You don't have to write all this down. Just want you to show you. Here's another system. And notice I've gone back to x, y, and z instead of x1, x2, and x3. But okay, so x, y, and z are unknowns. What are the values of x, y, and z that will satisfy all 3 of these equations? Okay, well, that's a tough order. What we're going to do is, the process is to eliminate one variable from 2 groupings, so to speak, of the equation. So I get down to 2 equations and 2 unknowns. And I look and I say, in the first equation, for instance, I have x's coefficient of 1. So if I just do corresponding multiples and add multiples of that first equation to the second and third equation, I can get rid of my x variable. So I can do -2 times the equation 1 and add that to equation 2, right? So what happens? -2 times this equation I have 2x plus a negative 2x. What's that leave me? 0. You see it's now gone. Of course I have 3y plus a negative 2y. What's 3y plus a negative 2y? That's 1y. Negative z, and then multiply by negative 2 here. Negative z and negative 2z, add those together. Negative z and negative 2z is negative 3z. And then negative 2 times 4 is negative 8. 1 plus a negative 8 is a negative 7. You see how that changed that equation? So I can do that. That's a valid operation. The solution to this system right here that I have written down here is the same as it is for up here. They're equivalent systems. But I've eliminated that x variable from this second equation. Okay. Now, if I'm looking at the augmented matrix over here, this is the corresponding augmented matrix. I hope you see that, right? Coefficients are what? 1, 1, 1, and then 4 is the constant term. 2, 3, negative 1, 1. I think everyone understands how we're doing that, right? So if I add negative 2 times row 1 to row 2, I get this, which is the corresponding thing we did over here. So here I would do 2 plus what? Negative 2 times 1 is negative 2. 2 plus negative 2 is 0. 3 plus negative 2 is 1. Negative 1 plus negative 2, negative 3. And then 1 plus what? Negative 2 times 8, negative 4. 1 and negative 4. 1 and negative 8, rather, is negative 7. And you see, I mean, it's the same thing we're getting here, but we're just kind of, this way we're just dealing with an algorithm where we can deal with just the numbers, the coefficients, and the constant terms. Okay. Now I can also eliminate this 3x by doing what? Add negative 3 times equation 1, so multiply the equation 1 by negative 3, and then add equation 3 to that new equation. So negative 3 times equation 1 added to equation 3. And when I do that, what? 3x and negative 3x is 0. Negative 4y and negative 3y is negative 7y. Negative 5z and negative 3z is negative 8z. And negative 3 times 4 is negative 12. 3 and negative 12 equals negative 9. And the corresponding row operation is what? Negative 3 times row 1 added to row 3. So if I do negative 3 times this row, add it to this row, that gives me this new row down here. Okay. So you see how this is tracking? And again, this equation here, this is the augmented matrix now. Okay. And now, if I look in these two equations, I have now 2 equations, 2 unknowns. All right. Now I can solve it like I did before. Okay. One thing I can do is, again, elimination again. Now I'm down focusing on these guys. I got y and z, so I can eliminate y by doing what? Adding 7 times row or equation 2 to equation 3. All right. When I do that, I'm going to zero that out. All right. So 7y and negative 7y is 0y. 7 times negative 3 is negative 21 plus negative 8. Negative 21 and negative 8 is negative 29z. And so on. All right. So 7 times this is negative 49. Negative 49 and negative 9 is negative 58. And here's the same thing I'm doing here. Add 7 times row 2 to row 3, and we get this corresponding thing. Right? And at this point you say, well, now I have this equation. I can solve for z. How would you solve for z here? You'd say, well, if negative 29z equals negative 58, I would divide both sides by negative 29. Yeah, you divide. But we can also multiply by what? The reciprocal. It's the same thing. Multiply by negative 1 over 29. Right? I can multiply that equation by that and solve for z. Of course, here's the corresponding row operation. So the row operation would be just multiply row 3 by negative 129. Okay? And when I do that, all right, when I multiply that last equation by negative 129, of course I get z is equal to 2, and in negative 129 times row 3 gives me this new row. Right? At this point I could stop now, notice, and I could solve the system by back substitution, because I know z is 2. So what is y? Well, if I replace z with 2 here, y minus what? 3 times 2, y minus 6 is negative 7. I can add 6 and I can solve for y. Okay, and once I get y and z, I can plug in y and z up in this first equation, and I can then solve for x. You see how that works? Back substitution. Start from the bottom up, so to speak. It's called back substitution. Okay, but another thing I just want to show you we can also do, we can proceed as follows. I can eliminate the variable z now from my first and second equation, okay, by using the fact that I can do multiples of this third equation. So to get rid of the z in the first equation, I can just multiply the first equation by -1 and add that to the first equation. Sorry, multiply the third equation by -1 and add that to the first equation. So -1 times equation 3 added to equation 1. And then I can get rid of this -3z by what? Multiplying 3 times this third equation and adding it to this, right? Since there's no values of y and x, I'm not going to affect these values of y and x at all, right? So if I do that, of course, the corresponding row operations are what? -1 times row 3 added to row 1, and 3 times row 3 added to row 2. Okay, and that's going to make this become 0 and that become 0. And here's what it looks like after that. Here's what it looks like after that. And so now notice I've got rid of the z variables in all but the last equation. And now I also know that y is equal to -1. Z is 2, y is -1. I can also eliminate this y by doing what? Add -1 times row 2 now, where this is 1y, to row 1, and that will get rid of this y here, and I'll have x all solved by itself. And when I do that, I get this, right? Similarly, -1 times row 2 added to row 1. So -1 times row 2 added to row 1. So I've got 1 plus -1 times 0 is still 1. 1 plus -1 times 1 is -1. 1 plus -1 is 0. 0 plus -1 times 0 is still 0. And 2 plus -1 times -1 is 2 plus 1, which is 3. And that's how that's working. But now, when you get to this stage, right, here's the augmented matrix. Clearly this says, 1x plus 0y plus 0z equals 3, which is x equal 3. And you can see here clearly we get the solution. Here it is. X is 3, y is -1, z is 2. There is our solution. So that's sort of the way, the process we're going to learn. The algorithm we're going to learn, though, is we won't be doing it. We won't be writing out the equations and doing all this stuff here. We're going to focus on the augmented matrix. So we're going to start with the augmented matrix, and we're going to try and get it into a particular form, doing just these row operations that are valid, because we know they're valid over here for the equations. And basically, two important forms that we would like to get it into are either this form here, which we'll see is called a row echelon form, and in that form we can then use back substitution, as we said, to solve the system, or we can take a look at getting down to this form, which is what we sometimes call a reduced form, or reduced row echelon form, and that form will give us the solution out like this. And of course there's going to be different looking situations. This obviously tells us we have one solution to the system, just exactly one solution, but we could have a situation again where there's no solution, or as we saw, infinitely many solutions. And so that's what we're going to look at in the next lecture. We're going to talk about a method known as Gaussian elimination and Gauss-Jordan elimination. Those two methods to solve a system of linear equations, and basically is exactly what we've done here. We're just going to get some terminology and go over the explicit form of the algorithm. So that's what we have in store for us next.